Hello and welcome to this fourth lecture of the course Basics of Semiconductor Devices and Technology. In this lecture, I will cover a few numerical problems on the module that I concluded in the last lecture, which was Origin of Quantum Mechanics. And the idea of these numerical problems is to give you a clear idea on or a clear perspective or the context on various theoretical aspects that we covered in the previous module, and you understand how and where to apply these concepts to gain a better understanding of the system under consideration. So let's do a quick recap before I get into the numerical problem discussions. So the last modules I covered, for instance, blackbody radiation. The blackbody radiation, we had looked into the following formulations. The very first one was given by Stephen, and what he said that the total radiation which you define by term P is equals to A sigma T to the power 4, where A is 1 for if you have a perfect black body, else it's less than 1, and sigma is the Stephen constant, and that's 5.67 10 to the minus 8 watt per meter square Kelvin to the power 4. So this basically tells the total radiation, which was basically the area under the curve, which is energy density per unit frequency. So if you plot energy density per unit frequency, which is as a function of frequency and temperature, and if you calculate the area under the curve, this is what you get. Now then, as I told you, that people were trying to fit this curve, and then there were two different approximations given. One was able to fit the high frequency part, and the other could fit the low frequency part. Now these two were, one was given by Wien, and Wien's formula for the energy density per unit frequency was A nu to the power 3 minus beta nu T. Now here A and beta are fitting parameters. Okay, and as I said, this only fits the high frequency. So I'll say high frequency data. Okay, and then the other one was given by Rayleigh-Jean. And again, in this case, the energy density per unit frequency, here this is frequency and this is temperature, was given by the formula 8 pi nu square divided by c cube and kT. You remember this kT was basically the average estimated energy of the system. Now and again, just to recollect, here the assumption was that the exchange between radiation and matter is continuous in nature, and that's why you see this term kT derived by the integral of the overall energy of the system. And then Planck pitched in, and he gave this formula by assuming that the interaction of energy and radiation is quantized, and it happens in this quantized entity, or the quantum of energy, which was given by the only difference was in the later part, and then you have nu spun. So this is the of a quanta, right? And the idea was that the energy exchange between the matter and the radiation would happen in this in the quantized fashion. Okay, so this was all about the black body radiation. So you recollect this formula, and we'll also see later on that how for lower frequencies and higher frequency this easily translates into Rayleigh-Jean or the Wien's formula respectively. Then after that we looked into the photoelectric effect. So this is something which was given by Einstein, and if you remember, we had typically a metal surface with a work function of W. The work function is defined in electron volts. Now you had this incident light with the energy equals to h nu, right? And then you had the kinetic energy of electrons. If h nu is greater than W, and this kinetic energy of the electrons could be h nu naught, where nu naught is the you can say that the frequency of, or h nu is the kinetic energy of the electrons which are ejected. They all are in electron volt unit, right? So the formula was h nu naught, which is the kinetic energy of the electrons which come out of the metal surface, is h nu, which is the kinetic which is the energy of the incident photon minus the work function. And you can also say that if this is the kinetic energy, then kinetic energy we all know is half mv square, and this velocity, this v, is the electron velocity, right? We also remember that the number of electrons emitted, let's say the number of emitted were proportional to the intensity, and the intensity is nothing but the number of photons, where each photon has the energy h nu. Keep in mind, just make a note, this is V and this is nu, which is frequency. This h nu can also be written as Sc by lambda. Then we had Bohr's atomic model. And what we learn here is that you have a nucleus with a positive charge, then you have these various orbits, and the electrons if they basically, there won't be any photon emission, or the release of the energy or the absorption of the energy, if the electrons are orbiting in their respective orbitals. But if there is a transition from one orbital to the other, for instance, let's say if an electron moves from the higher orbital to the lower orbital, and if this orbital has energy Em and this is En, then due to this transition you will have a photon emission with energy h nu, and the relation will be that Em minus En equals to h nu. The similar will happen if you basically, if you give an energy h nu to an electron which is in an inner orbital, this can move to an outer orbital with higher energy. Then subsequently we looked into wave particle duality. So here the idea was that in the wave particle duality, the proposal was that with every particle there is a wave associated, and every wave behaves like a particle, and the relation which connects this, which was given by De-Broglie, was lambda equals to h by p, where p is the momentum, so you all know momentum is mv, here v is the velocity. So you can write lambda equals to h by mv, and I mean, this was derived by simple formula that P is nothing but the energy or the kinetic energy divided by speed of light in this case. So kinetic energy is h nu divided by c, and this becomes h lambda. If you rearrange, it becomes lambda equals to h by p. There are a few other things that you should remember. I told you earlier that the kinetic energy is nothing but half mv square. Now if I try to rearrange this, I can write it as half m square v square divided by m. Now you see this is nothing but mv square, which is momentum square. So I can write this as momentum square divided by 2m. And if I take this to the other side, it becomes momentum square equals to 2m. If I write kinetic energy just as k, so this becomes momentum equals to square root of 2mk. This is something which we are going to use subsequently. Now keep in mind that this k is in electron volt. So now if you have, if you have a problem where it says that there's a plate with a voltage V applied between this, and the electron is getting accelerated because of this potential difference which is V, the energy of the electron, let's say if this is negative and this is positive, the energy of the electron as it reaches close to this point will be close to charge times voltage, electron volts. Okay. Now finally we have the uncertainty principle. So what it says, you take two reciprocal entities, let's say position and momentum, and the error in measuring the position and the error in measuring the momentum will always follow this uncertainty relation, which means the product of the two errors will always be greater than h bar by 2, where h bar is h by 2 pi and h is the Planck constant. The same is valid for other reciprocal entities like the energy and time. So you have delta E times delta T is greater than equals to h bar by 2. So this is all what we covered in the previous modules. So make a note of this, and we are going to use some of these mathematical formulations in the numericals that I'm going to cover subsequently. Okay, so now let's look into the problems. So the first problem is that let's say show that Planck's formula reduces to Wien's formula in the short wavelength limit and Rayleigh-Jean's formula in the long wavelength limit. So short wavelength means we are talking about lambda being small, and if lambda is small, you remember that the Planck's formula was T equals to 8 pi nu square c cube, and then we had h nu divided by e to the power h nu by kt minus 1. So if lambda is small, we know the bottom part can be seen as this. So this is going to be greater than 1. So the second half of this equation, which is this part, will get converted to this, right, times h nu. Now if you see, this is very similar to the Wien's law. On the other hand, if lambda is large, this entire thing will be, the bottom part can be written as 1 plus hc by lambda kt. Now if you multiply the energy density per unit frequency will get converted to something which is similar to the Rayleigh-Jean's formula. In Rayleigh-Jean's formula, you remember you had this term, and then you had this kt term, which was the expected energy of the system. Let's go to the next one. So the next problem is that we have to find the number of photons. So make a note, photons emitted per second by a 40 watt power source of monochromatic light of wavelength 6000 angstroms. So monochromatic light means you have a source which emits light having a fixed wavelength, and in this case the wavelength is given as 6000 angstroms. Now what you have is the power source which has the power of 40 watts. So this is power, and we all know that we deal with energy, right? And when we deal with energy, we know the energy of a single photon is h nu. So since we have the wavelength, we can calculate nu from this. Now h nu is the energy of a single photon, and let's say if there are n number of photons, which is the number of photons, and let's say if this number of photon is n, then the total energy of photon will be n times h nu, which is here. Now this is energy. How do we calculate energy from the other side where we have the power source? So that's why you see the term emitted per second, and you know that when you integrate power with time, you get energy. So in this case, we assume that the power source is constant. So the integration is nothing but multiplication of with that time. So you have power times that amount of time. In other words, this is p dt 0 to t, and if the power is independent of time, then this is nothing but p times t, and here p is 40 watts and t is 1 second. So this gives you the energy, right? So now we got the energy, which is 40. Now you can equate. So N will be E divided by h nu, or E times lambda divided by h c. So you feed all the numbers, and just rub here. So you feed all the numbers, and what you get is in 1 second the source will emit 12.06 into 10 power minus 19 number of photons. Okay, let's move next. The next is find the frequency of light. Now here the question is slightly different. Find the frequency of light. So we are talking about finding the nu, which ejects from a metal surface, where the electrons fully stopped by retarding potential of 3 volt. So what we have to find the frequency of light which will eject from a metal surface. What is going to be ejected? Electrons, and these electrons will be stopped if you apply a retarding potential. You remember the setup which I had shown. So this 3 volt is basically the voltage applied opposite to the flow of electron. The photoelectric effect begins in this metal at a frequency which is 6 into 10 power 14 per second. Find the work function of the metal. So if I draw a schematic to explain this problem better to you, let's assume that you have a metal plate and you have incident photon on this. There's another metal plate, and now I apply. So if there's no field, so let's say this is the potential, and if there's no field, the electrons will be ejected and they will move with a kinetic energy in the other direction. Now if I apply a potential which is, let's say, of 3 volt, let's say 3 volt, what's going to happen is that these electrons will stop, they will be retarded, and they won't reach to the other side plate. So what does this mean? That if this 3 volt is the retarding potential, the kinetic energy of these electrons given is charge times 3 volt. So this is actually 3 into E electron volts, right? The other aspect given is you have the threshold frequency of the metal given. So you know that the work function is nothing but this times Planck's constant, and that will give you the work function. And then if you bring this to the photoelectric effect, then we know that the kinetic energy of the emitted electron is nothing but the energy of the incident light minus the work function. The kinetic energy is basically charge times the potential which was, let's say if this is V naught, applied in this setup, equals to h nu, which is the energy of the incident photon, minus h nu naught, where nu naught is the threshold frequency of the metal. So if you feed these values back, if I rub this for simplicity, and if you feed these values back, what you get, the work function of the metal is 2.486 electron volts. And now I would feed this value back here. So this is the work function, and this value is already known to us, and what we have to find is this nu, which is the frequency of the light which is incident on the metal surface, and we feed that value back. We arrange this, the nu will turn out to be E times potential plus h nu naught divided by Planck's constant, and if you calculate this, the frequency is going to be 1.32 into 10 power 15 per second. Let's move to the next problem. So the next problem is that you have a light metal, sodium, and the work function of sodium is given as 2.3 electron volt. Now the question is, would sodium show photoelectric effect if the incident light has a wavelength of 6800 angstroms? So all we have to find is the energy of the incident light, and if this energy is greater than, so this will correspond to a certain h nu, and if this h nu is greater than 2.3 electron volts, then yes, there will be a photoelectric effect. If it is not, then they won't be. So we have the wavelength, and then from wavelength we know the energy of the incident photon, which is h nu or hc by lambda. You feed all the values, you find that the energy of the incident photon is 1.83, and since the energy of the incident photon is less than the work function of sodium, the photoelectric emission is not possible with the given light source. Let's look into the next problem. Now you have a light source of wavelength 3500 angstroms, which is incident on two metals, A and B. Now you have to basically find which metal will yield a photoelectric effect, or basically which metal will eject these electrons or photoelectrons. Now if the work function of metal A is 4.2 electron volts and metal B is 1.9 electron volts. So all you have to find is what is the energy of corresponding to this wavelength. So you have to find energy, which is E equals to hc by lambda. Lambda is given to you, so you can find the energy. So if you feed all these values in the formula, the energy turns out to be 3.53 electron volt. Now this is less than the work function of metal A, right? So let's say if this is E, then E is less than the work function of metal A, but is greater than the work function of metal B. So it means that metal B will show photoelectrons, but metal A will not. Let's go to the next problem. Now you have to find the maximum kinetic energy of a photoelectron in electron volts emitted by shining light of wavelength 6.2 into 10 power minus 6 meters on a metal surface. The work function of the metal is 0.1 electron volts. So what do we have? We have the wavelength and we have the work function of the metal. And what we have to find? We have to find the energy of the ejected electrons, and you all know that energy of the ejected electrons is h nu, or in this case hc by lambda. This is for the incident photon minus the work function which is 0.1 electron volts. Now we feed the values here. This is the equation which I was talking about. We feed the values. We find the energy of the ejected electrons is 0.1 electron volts. Let's look into the next problem. The light emitted by a 1 milliwatt helium neon laser source. So here you have a laser light. Doesn't matter, you have a light source. Laser means you have a fixed wavelength, and the power of the light source given as 1 milliwatt. Earlier we had dealt with a problem with 40 watt power source. In this case it's 1 milliwatt, and you would like to basically attenuate this by a factor of 10 to power 11. So we are saying that now I would like to attenuate the intensity by 10 to power 11. The attenuated light is sent into an aluminum box of length 80 centimeter. How many photons do you expect in the box at any instant of time? Right? As you see, this problem is very similar to the one which we addressed earlier, but there are some additional aspects. For instance, you may say that I don't know the wavelength of the light source, but what we see here is we have the nature of the light source given. It is helium neon laser source. So if you search, you will find helium neon laser source is nothing but a source of 633 nanometers laser light source. What you also have is 1 milliwatt power, but we are putting an attenuator in between, and the attenuation factor is 10 to the power 11. What does this attenuation means? It is basically reducing the number of photons which are emitted beyond the attenuator by a factor of 10 to the power 11. Right, so now per unit, the energy output through the attenuator, earlier what we did, we multiplied power with the time, and if it is energy, we are taking time as 1 second. Power is 1 milliwatt, but now we have an attenuation factor, so we are going to multiply this with the attenuation factor. So this is the total energy output of this laser plus the attenuator system. Now this is the total energy that we have. Now you know that you can calculate the number of photons by equating this with, let's say you have n number of photons times h nu will be equals to this. So n, which is the number of photon, n is going to be 10 to the power minus 14 divided by h nu or hc by lambda, and this lambda is 633 nanometers, right? So we can get the total number of photons which are emitted per unit second. Now this is per unit second. Now we have a system where the photon has to travel length which is 80 centimeters. So we'll try to find how much time a photon will take to travel this much length, which means that number of photons present inside this box would nothing be but it would be n, which is the number of photons per unit second, times the time the photon stays. The time the photon stays, let's say if this is the total travel time is t, right, and the number of photons entered is n per unit second, then the number of photons which stays inside is nothing but n times t. So let's see. Let me just rub this. So as I said that we find the energy of the light source. So basically 633 is the wavelength of the light source. So the energy of each photon is going to be your hc by lambda, and hc is nothing but 1240 electron volt nanometer divided by 633 nanometers. So this becomes 1.96 electron volts. You can convert this to joule, and therefore the number of photons which are entering the tube per second is nothing but the energy output through the attenuator divided by the energy of a single photon. So this is the number of total photons that are entering this 80 centimeter long box. So let's say this is n. Now the time taken by the light to cover, as I mentioned earlier, the time is nothing but the length divided by the speed, in this case the speed of light. So this is the length and this is the speed of light. So you see that a photon, when it enters this box, it will take t amount of time, which is 2.67 into 10 power minus 9 seconds. So the number of photons which stays inside this box in t amount of time is the number of photons entering per unit second times the time which is for which we have to integrate. So the time available is small t. So the number of photons, let's say the number of photons stays inside is n. So n is nothing but n times t. So anytime the number of photons present in the tube are the same as those entering the tube within this time, and so basically we are talking about this n. So in this case the n is small n, it's the same as this capital N which I denoted, and this the numbers are less than 1. So since this is less than 1, which means that you will not have more than one photon at any given instant of time staying inside this box. Okay, let's move to the next problem. So what should be the frequency of incident radiation to eject electrons of maximum speed of 10 to the power 6? Consider this as meter per second for potassium metal. Now you have the speed of the electrons which are coming out. We all know that from speed we can calculate the energy, which is half mv square. You have the potassium metal, so the work function is known, which is 2.26 electron volt, and all you have to find is the frequency of the incident radiation so that you get this kind of speed. So we know that the kinetic energy of the electron which comes out, in this case half mv square, is nothing but the energy of the incident radiation, which is h nu, minus the work function. So if I rearrange h nu, which is the frequency, which is the energy of the incident radiation that we are looking for, is nothing but the kinetic energy of the electron plus the work function. So nu is nothing but the kinetic energy plus the work function divided by Planck constant. So we rearrange everything and we put into this equation, and you get nu equals to 1.23 into 10 to the power 15 hertz. Okay, let's move to the next problem. You have work function of the metal given, and you see this is given in joule. Now you have to find the threshold frequency for photoelectric emission. So the work function is given. We have to find, from this work function, we have to find the energy in electron volt, and we know this electron volt is nothing but the h nu, or in this case h nu naught, and this h nu naught is the threshold frequency. So if we convert this from joule to electron volt and divide by Planck constant, we get the threshold frequency. The other is, if the metal is exposed to a light beam of frequency 6 into 10 to the power 14 hertz, what will be the stopping potential? So stopping potential as we have seen earlier, is nothing but the reverse of the kinetic energy. So from the kinetic energy, if you have kinetic energy and if you divide this by the charge on the electron, you get the stopping potential. That's what we have seen earlier, right? So which means we have to find the kinetic energy of the electron which comes out if the light has incident light's frequency is 6 into 10 power 14 hertz, right? So first we find the threshold frequency and then we feed back into this formula, get the kinetic energy, and then from kinetic energy we get the stopping potential. So let's do that. So work function, as I mentioned, is h nu naught. Nu naught is the threshold frequency. So threshold frequency is nothing but basically phi by h. In this case, the phi is the work function, so the h goes to the other side, it becomes phi by h, right? And the phi is given, h is Planck constant, we all know, so the threshold frequency comes out to be 3.8 into 10 power 14 per second. Now for the frequency nu, associated energy is h nu, is what we all know, and therefore if we feed the nu into it, which is given, the energy comes out to be 3.9 into 10 power minus 19 joule. Therefore the kinetic energy of the photoelectrons, which is nothing but this E minus work function, which is here, you get 1.2 electron volt. And as I said, if this is the kinetic energy, you divide by, if this is the kinetic energy, you divide this by charge, and you get this stopping potential. So if this is 1.2 electron volt, you divide this by electron, so electron cancels, you get 1.2 volt as the stopping potential. Okay, now here is something interesting, and before I get into that, you should know that when a charged particle is sent perpendicular to a magnetic field, it goes in a circular arc of radius, where the radius is given by mv by qb, where v is the velocity and b is the magnetic field. So the problem is, a beam of 450 nanometer light, so you get the wavelength here. So you get the wavelength here, is incident on a metal having a work function 2 electron volts. So you have the work function. From this wavelength you can calculate the energy of the incident light source. You get the work function. So from the difference you can find the kinetic energy of the electron which is coming out. Now the catch here is, the tricky part here is that you have a magnetic field placed in the system. Now you know that the most energetic electrons, so when they are emitted and perpendicular to the field, they will be bent in a circular arc. So you have these electrons and you have magnetic field, so these electrons will start revolving, and this radius is given as 20 centimeters. Now you have to find the value of B. So the first thing first, we find the kinetic energy of this most energetic electron. The kinetic energy is nothing but the energy of the incident photon minus the work function. The photon's wavelength is given as 450 nanometers. So the energy of the incident photon is hc by lambda, and the work function given as 2 electron volt. So you do the difference and calculate the kinetic energy in terms of joules, which is 1.2 into 10 power minus 19 joules. Now, as I told you that when a charged particle is basically is placed perpendicular to the magnetic field, so basically the charged particle has a certain energy, right? And let's say if the magnetic field is normal to the paper, and then you have this charged particle with a certain kinetic energy, so it will get bent and it will start revolving, right? And we have to find this we have this radius given, so we have to find what is this magnetic field, right? So the radius is given by this formula mv divided by q times b, and we have to find b. So you can rearrange this, and b apparently becomes mv divided by q times r. Now if you notice, this mv is nothing but the momentum of the charged particle. So you can calculate the momentum. We have seen this this relation earlier, where momentum is nothing but under root of 2m and the kinetic energy, and that's what we are doing here. The momentum is 2 times under root of 2m kinetic energy. So you calculate the momentum and you feed this momentum here in this formula, and you get the magnetic field. In this case, the magnetic field turns out to be 1.46 into 10 power minus 5 Tesla. Okay, now the other problem is that we have a stopping potential of 0.82 volt. So the stopping potential, again, you remember the setup where we apply a reverse potential to stop the energetic electrons, and this stopping potential is nothing but is a measure of what is the kinetic energy of the electron, right? So the stopping potential of 0.82 volt is required to stop the emission of photoelectrons from the surface of a metal by light of wavelength 4000 angstroms. Now you have to find the value of Planck constant. I mean, we know Planck constant, but let's derive it. I mean, that's how these constants were derived in the past, right? So you have to find the value of the Planck constant. If the stopping potential is 1.85 volt for the wavelength of 3000 angstrom. So you can think of this as an experimental setup where you are trying to basically find the Planck constant. You say that, okay, this energy is some constant times the frequency. You don't know what is this constant, and you're trying to derive this constant. So you have this setup where you have this incident light on this metal surface, and it's the same metal surface, keep that in mind, so with a work function W. And now you apply a voltage. Now if there is no voltage, these electrons will move with kinetic energy Ke, and but if you apply a potential, let's say equals to V0, and a reverse potential, so that this repels electrons. So this plate, the right side plate, must repel the electrons, and therefore it should retard the energy or the kinetic energy of the electrons. And if this retarding potential is equivalent to the kinetic energy of the electrons will not be able to reach the other side of the plate, right? So what we are doing here is we are basically running this experiment for different light sources. The work function is fixed. The light source, this has, we have h nu 1, we have h nu 2. So from all of this we are trying to extract h. Let's see how do we do it. So let's say in the first case, when the energy, the light source is having wavelength lambda 1 equals to 4000 angstroms, the equation will be hc divided by lambda 1 equals to E times V1, which is the retarding potential, and for lambda 1 of 4000, retarding potential is 0.82, and for lambda 2 of 3000, the retarding potential is 1.85. The work function is fixed in both the cases. So we can rearrange this by subtracting both sides of this equation. Let's say this is equation 1 and this is equation 2. So if you subtract, what you get is hc 1 upon lambda 1 minus 1 upon lambda 2 equals to E times V2 minus V1. We have lambda 1, we have lambda 2, we have V2, we have V1. We know C, So with this we can calculate H. Now H turns out to be what we all know as the value of the Planck constant. Now once this is there, then you can feed this back into one of these equations, and you can also calculate the value of W. So now this problem tells you how experimentally, these work functions and the value of these fitting parameters or the constants like Planck constant. I mean, later on it was named as Planck constant, but at that time it was constant. So how these constants and other parameters were experimentally derived. So the other question was, at the stopping potential of the wavelength of the incident light is kept fixed to 4000 angstroms, but the intensity of the light increased by 2 times. Will the photoelectric current be obtained? Give reason for your answer. Right. So, I mean, of course not, because it doesn't depend on the intensity of the light and only depends on the wavelength. Okay, so let's look into the next problem. Here the light of wavelength of 4560 angstroms with a power of 1 milliwatt is given, is incident on, let's say, a surface you have on cesium surface. And what you have to find is you have to calculate the photoelectric current assuming a quantum efficiency of 0.5%. and work function of cesium is 1.92 electron volt. Okay, so what do we all have here, right? We have the power of the light source, we have the wavelength, and we have the work function, and we also have a term which is the quantum efficiency. The quantum efficiency tells that how many photons are going to basically give you the photoelectric current or photocurrent, right? So which means, let's say if you have n number of photons which are incident on the surface, only 0.5 of those n number of photons are going to be responsible for or going to offer you the photoelectric current, right? So then let's get to the job. We know the energy of one photon is h nu or hc by lambda. So what do? We calculate the number of photons incident on the surface per second, and if only 0.5% of the incident photons are released, are responsible for releasing electrons, therefore we can calculate how many electrons are released per second, right? So let's see. The energy of the photon comes out to be 4.32 into 10 power minus 19 joules. And if you just divide this, use this and divide, the energy is 1 milliwatt times time 1 second. So basically 1 milli electron volt and 1 millijoule, sorry, and you divide this by the number that we already have. So you get 2.31 into 10 power 15 photons per second. Now the quantum efficiency is 0.5%, so only 0.5% of this number are going to basically offer you photocurrent or going to release the electron. So the total number of photons which are going to offer you the photocurrent is 1.16 into 10 power 13 per second. Now the current is nothing but charge times number of electrons per unit second. So if these are the number of photons which will give you the number of, which will release the electrons, and that you get 1 electron per photon. That was the idea, where the number of electrons were dependent on the intensity. So you get these many electrons per unit second. So now if we multiply this number of electrons per unit second by the charge, we get the total current, and the total current turns out to be 1.86 microamperes. Okay, so now let's switch gear and we now talk about De-Broglie hypothesis and what we can derive out of it. So the question here is that what should be the velocity of an electron if its de Broglie wavelength is 1 micrometer, right? So de Broglie wavelength is nothing but the wavelength associated with the particle. So let's say if you can think of each particle, each object. Let's say this is the object, and with each object there would be some wavelength associated with it, right? You can also think of this wave as the probability density of finding this particle, right? So if the wavelength is bigger than the size of the particle, which means that the particle is not the presence of particle, or the location of particle is not certain, it would fall into certain probability window. But if you take a very big particle like a bullet or anything else that we can see with the bare eye, you would notice that the wave associated with this would be so small compared to the size that if you calculate the probability density, the probability of finding the particle will be same place as you find from the classical understanding or classical physics. Right. So let's see, and we will see in some of the problems that how these things matter. So for the time being, whenever this wave aspect comes into picture, you can think of this wave as, and we'll also see this in the quantum mechanics lectures later on, that you can see this wave. So let's say if you have a certain wave associated, I mean, the wave function could be anything. I mean, it could be something like this. Let's say this is the origin. It could be something like this, where this is where the particle is, right? Or it could be something like this, or it could be something like this. It could be anything. The wave shape could be anything. But you can think of this wave as some mathematical representation of the probability density, like where the probability of finding the particle. And if this wave is much bigger than the size of the particle, then you know that though the particle is classically somewhere here, but in reality, quantum mechanically, it can be anywhere in this large window. But if this particle is much bigger than the wave associated, then the probability of finding the particle or the object extracted from quantum mechanics will be same as what you get from the classical physics. Okay, so let's again look into this problem, and I rub this here. Okay. So we have seen earlier, momentum P was given by h by lambda. So you can rearrange, and lambda is h by p. P momentum is nothing but mv. So we have lambda given, we have h given, we know the mass. So all we have to do is find the velocity. So the velocity, and now if it is an electron, the h by m times c is 2.4 picometers. So you can calculate if it is an electron, the velocity is going to be 720 meter per second. Good. Let's look into the next problem. What is the de Broglie wavelength of electron moving with a kinetic energy of 100 electron volt? Simple. We have seen this formula earlier. Lambda equals to h by p, and p is nothing but 2 times mass times kinetic energy, and the kinetic energy is given as 100 electron volts here. We know the mass, we know the Planck constant. We can find lambda, right? So the lambda comes to be 1.2 into 10 power minus 11 meters. Now you see that if an electron is moving with an energy, and 100 electron volt is very small energy, when we talk about subatomic particles. And if you see, the size of the wavelength associated with the electron is much bigger than the size of the electron. I mean, the size of the electron would be much smaller than an angstrom or a picometer or whatever, right? Whereas the number that you get here, the wavelength associated with that, is close to 1.2 angstroms, right? So in reality, if this is your electron, the wave associated with that is something of this sort. So now you don't know where the electron is. If this wave function is the probability, is representation of probability density, your electron can be present anywhere in this region. Now it's the same problem again. So in this case, you have you have to find the De-Broglie wavelength of an electron accelerated through a potential difference of 100 volt. And if it is 100 volt, then the corresponding energy is going to be 100 electron volts. And we have seen this earlier. So we have seen this formula, lambda equals to h by 2m kinetic energy, and kinetic energy is nothing but E times V. So this formula becomes h divided by 2me into 1 upon under root V, and we know this being a constant, which is 12.3. So we feed all these values back, and what we get is 1.23 angstroms, which is the same value which we saw in the previous problem. Okay, now an electron in a hydrogen-like atom is in an excited state. It has the total energy of 3.4 electron volt. Calculate the kinetic energy and the De-Broglie wavelength of the electron. So kinetic energy is nothing but the energy of the electron in the excited state. If it is not in the excited state, there is no kinetic energy. I mean, the energy of the electron would be zero, and the system would have a net potential energy. So if the electron is in the excited state, the energy of the electron in the excited state is the kinetic energy of the electron, right? So that basically solves the first question. And what is the De-Broglie wavelength of the electron? So if you know the kinetic energy, we know the De-Broglie wavelength is nothing but h by under root 2m, and this kinetic energy is 3.4 electron volts, right? So you feed the value, and what we get is 6.663 angstroms. Again, you see that in this case, for instance, an electron which is in the excited state with energy just 3.4 electron volts, get a wavelength associated with that close to 6.663 angstroms, which is even bigger than Bohr's radius. So you can imagine that the electron could exist anywhere in this particular window, and this window is much bigger than the size of electrons. So when you go to the subatomic or atomic or subatomic particles, now you cannot predict their behavior, or let's say position or momentum, using classical understanding of the physics. Now we see that how this basically the quantum mechanics results into what we know from classical physics when we talk about macroscopic objects, right? So you have a ball, and let's say the mass of the ball is 100 grams, and that's moving with a speed of 1 meter per second. Now you have to calculate the De-Broglie wavelength associated with it, and can the effect of this wavelength be observed experimentally? So let's calculate the De-Broglie wavelength. We know the wavelength is h by p. P is mass times velocity, which is momentum. So we feed this back, lambda equals to h by mv, and you feed all the values. You know the Planck constant, you know the mass, and you know the speed, right? So what we get for this kind of object, the wavelength associated with this is 6.63 into 10 power minus 32 meters. Now any ball with a mass of close to 10 grams would be of the size of at least few millimeters or close to a centimeter. Now compared to the size of that object, right, the wavelength associated with this is so small that you won't notice it, right? You can't experimentally notice it. So even if you calculate the probability density or probability of finding this particle, the probability of finding the particle will be same as what you actually get or what you actually see by bare eyes, which is the classical world, or the the estimations from the classical physics. Okay, now calculate the De-Broglie wavelength of thermal neutrons. You get the temperature, so from the temperature you can calculate the kinetic energy, and you have the Boltzmann constant given with you, right? So how do we calculate the energy? We have these are thermal neutrons, so the energy is nothing but kT, and T is this temperature, K is the Boltzmann constant. So you can find the kinetic energy, and then you feed this kinetic energy, which is nothing but kT, into this formula, which is lambda equals to h divided by 2m kinetic energy. You get the number, and here the wavelength associated turns out to be 1.78 angstroms. Now keep in mind this T is the absolute temperature. I will leave some problems for you to think about, and I would like you to basically go through these problems and give it a thought and try solving these problems on your own. You can pause and make a note. So I'll move to the next slide, and I give you the solutions as well, but try solving it first, and then you can take a look into the solution. Okay, so the next problem is you have a vehicle, right? I mean, the vehicle is 180 kilograms in weight, and of course you have a speedometer in the vehicle, and the vehicle speedometer reads 72 kilometers per hour as the speed at a particular instant, right? Let's say this instant is t naught, and the readings are known to have an accuracy of plus minus 2 kilometers per hour. Now this is speed, right? This is velocity. So this is nothing but delta velocity. What would the maximum uncertainty in the position of the vehicle? So what we have to find? We have to find the delta x. So we apply the Heisenberg's uncertainty principle, but first in the Heisenberg uncertainty principle, the equation is you have delta x, which is the error in the position, times delta p, which is the error in the momentum, is greater than or equals to h bar by 2, right? So we have to find delta x. First, let's calculate delta p. For delta p, we have the delta v, right? So delta p is nothing but delta of mv. Mv know is a fixed number, is a measurable fixed number. There's no uncertainty in that. Is not a reciprocal quantity with the position. So m is fixed. So then the delta momentum is nothing but m times delta velocity, which is given here. So m times delta velocity. So we calculate the m times delta velocity, and the delta momentum comes out to be 100 kilogram meter per second. Now we feed this back into the uncertainty principle, and what we find is the delta in the position comes to be 0.5 into 10 power minus 36 meters. So now you see that the Heisenberg's uncertainty principle is true even for the classical world or the macroscopic objects, but the numbers are so small that experimentally you cannot detect this, and therefore what we see with the bare eye turns out to be real, turns out to be precise to what we measure, right? You see the uncertainty in the position measured is so small compared to what we can notice with bare eye or any experimental setup in the world. Now let's try the same for the electron. So speed of an electron is given where the mass of the electron is this, and the speed of the electron is measured as 5 into 10 power 6 meter per second. Now this value, this speed is measured with an uncertainty of 10%, which means the delta in the velocity is 10% of this value. You have to estimate the uncertainty in the position. Again, the same aspect, same formula, we calculate the delta P, and delta P is nothing but mass times delta V, and delta V is basically 10% of the value given, which is 5 into 10 power 6 meter per second. And from this delta P, we feed this into uncertainty principle and we calculate delta X. So let's see that. So the delta P turns out to be, if we calculate with this approach as I mentioned, is 8.35 into 10 power minus 26 kilogram meter per second. Now we feed this value here, and what we see that the delta X is 10 to the power minus 9 meters. Now you see in the previous case the delta X was of the order of 10 to the power minus 34 meters, which is not observable from by any experimental mean, as well as the size, the delta, the uncertainty in the position is much smaller compared to the size of the microscopic object we were dealing with, and in that case it was a car. Now in this case the size, the delta X is quite observable, and this is much bigger than the size of or the length of an electron, and therefore the when you measure one of the parameter with a certain if you try to measure one of the parameter with as good as possible accuracy, you are going to lose the accuracy in the other parameter. That's what the uncertainty principle tells, and that's also what you see here, and this becomes noticeable for the microscopic object, subatomic or atomic particles, but the same is not observable as we saw in the previous problem for macroscopic objects. Okay. So let's look into the last problem of this this lecture now. This is a bit tricky. So what you have to do, you have to calculate the uncertainty in the momentum of a proton confined inside the nucleus of a radius 10 to the power minus 14. So you have a nucleus, and this radius is given, and you have a proton which is confined inside this. So as you know that this is like a particle inside an infinite potential well. So if I say that this proton would be oscillating this way or this way, so it would be forth and back motion in both the direction, which means that the error in the maximum error in finding the position of the particle would be nothing but this radius, right? So the delta X in this case is the radius. We will certainly find the proton somewhere in this half or somewhere in this half, which means that the maximum error possible in terms of finding the proton is going to be the radius of the nucleus. So delta X is the radius of the nucleus, right? So now if the delta X is known from the uncertainty principle, we can calculate the delta momentum. Now what we do is that this is the maximum uncertainty, but again if you find the mean uncertainty in the position, the mean uncertainty is going to be r by 2, right? So which is basically going to be radius divided by 2, right? So if we calculate, if you take the mean uncertainty in the position, or the average uncertainty in the position, and we feed that value back, we get the average uncertainty in the momentum, which turns out to be h bar divided by r naught. So we calculate this average, which is 1.054 into 10 to the power minus 20 kilogram meter per second. They are There are other approach as well. You can calculate the worst uncertainty in the position, and that will be R. So you can use R, and that will give you the worst uncertainty. You can also take R by 2, so that will give you the mean uncertainty in the in the position, right? So you get the delta P. Now we have delta P. The question is, what will be the least kinetic energy of the proton, right? So the least kinetic energy of the proton is linked to the least momentum of the proton. So if the uncertainty in the proton, in the momentum of the proton is delta P, we know that from various readings, one of the value of the momentum would certainly be equals to delta P. So we can say that the delta P could be the least momentum, and from this we can find the least energy of the proton. So taking the least momentum delta P of the order of, least momentum P to be of the order of delta P, the least kinetic energy would nothing be, as we know, E equals to momentum squared divided by 2m, and we have already got this relation here. So you feed the values and you get the number. So in this case, the energy of the proton, which is confined inside the nucleus, is close to 0.21 mega electron volt. And again, this is the least energy. What it tells that when the proton is oscillating between the walls of the nucleus, the minimum energy of this proton oscillation, or the proton which is moving between forth and back, would be 0.21 mega electron volt. So good. We come to the end of this particular lecture, as well as the module on the origin of quantum mechanics. I hope all these problems would have given you a much better perspective of the quantum phenomena, and how things are different in the classical world, and how things become different just because there are certain things we cannot observe, or there are certain things that we cannot observe in the classical world, and therefore whatever we see with the bare eye is the same as what the quantum mechanics estimate, versus when we try to observe the same thing in the subatomic world, you can't observe that by bare eye or any other mean without disturbing the system. And we also saw that the kind of wavelengths associated with the subatomic particles, and therefore everything becomes probabilistic in nature in the subatomic world compared to deterministic in nature when we talk about the macroscopic world. So with this, thank you very much, and now I'll see you in the next class, which will be the mathematical framework and the formalism of quantum mechanics, and we'll use that to solve several problems which are relevant to quantum mechanical world. Thank you.